This meeting is.
Good morning and welcome to this quick recording talking about chapter 18. Let me switch cameras to at least show the work area. Hold on. Oh man, I need to move the background. Okay. So we saw in chapter basically 17 the zeroth law, and the zeroth law basically allows us to define basically a way of measuring temperature. Okay. So from now on, we're going to assume that we're going to be measuring temperature and way for doing that. And most of the part, for at least for the most part for this chapter, we're going to be using the Kelvin scale. Okay. Prior to basically the formulation of thermodynamics the way that we know it today, there was a lot of work, and that work basically led to the following law. If I fix the temperature and I change the volume, the pressure changes accordingly, inversely proportional with the volume. And if I fix the volume, the pressure changes proportional to the temperature. And if I fix the pressure, the volume also is proportional to the temperature, and so on and so forth. For the so-called ideal gases, those are gases that meet special requirements in terms of their density and so on and so forth. So assuming that this is basically this is an experimental law, okay? So this is something that we know from observation. Today, chapter 18, we're going to attempt to understand how that works, okay? It's going to all rely on the work of Mr. Boltzmann. Does he have two N's in his name or a single N? I don't remember. Let me Google it to just make sure that I give you the correct name, the correct spelling at least. Boltzmann. Yeah, two N's, that's correct. Okay, so Mr. Boltzmann basically hypothesized the following situation that an ideal gas is made up of tiny particles. Remember, this is the time when it was in the late 1800s, before the discovery of atoms, molecules, or anything of that sort. So we didn't know about those things. So he made a leap of faith, trying to understand basically how these gases work. And in doing so, he made the hypothesis that they are made up of tiny particles. And those particles, they are so small that their sizes are negligible. Today, we know what they are. We know that they are molecules. But in the time when he was working on those things, there was not enough information about them. He made another assumption that of course, their sizes are so small that they are negligible compared to the sizes of interest, namely the cubic root of the volume. Okay. And also that they are free to move in the gas at will. And the only interactions that he considered, he took into account, was the fact that they collide with the surface of the container. Okay, that what he was about to show, that is the pressure that is measured by the devices. Okay, so imagine we have a cube in here of sizes, which I'm going to call A. So this cube is a fixed size. I know the book has a different approach to it, but there is an issue in terms of coming to the averages at the end, but this should work, okay? So we're going to focus on this direction, the X direction, okay? And whatever we find for the X direction, we should be able to use the symmetry, because he made another assumption that this gas also is an isotropic gas, meaning that, the distribution is uniform throughout space. So whatever we know happens in the x-axis must be happening in the y-axis and the z-axis. So we're going to focus on the x-axis. This surface of interest to us has a measure, and this measure in this case is just a squared, okay? So if I can find the force exerted by that gas on that surface, and if I divide, that gas on that surface, yes, and if I divide that force by the area and plug in a device in here to measure the pressure, that should be true in any surface I'm focused on. Okay, so I could take that device and put it on the this surface that is clearly perpendicular to at least the area itself, the face is perpendicular to the y direction. And if I do my analysis for the y direction, I should find the same measurements for the pressure because I'm assuming that it's uniform throughout space. So again, we're going to just focus on the x-axis, find this force divided by the area, and we would have found the measure for this pressure. So that's basically what his goal was, okay? At that time, we don't really know what the temperature was. We have an intuitive notion of what it is. We can measure it based on the zeroth law, but we don't know exactly what it represents. So in doing so, actually, he was able to interpret what that temperature measures. What is it exactly that we're talking about? And this is a big, big deal, okay? Okay, so let's think about this one. I'm going to take one particle specifically, a particle I, and it's moving in this direction, hits the wall somewhere, and then bounces off of the wall. As it bounces off of the wall, he made another assumption that all of the collisions with the walls are elastic collisions. Okay, to make the math easy. Okay, and the wall is immovable. So, meaning that the initial velocity, since the focus is on the x direction, so this is the Vx, the x component of the velocity of the ith particle as it's colliding with the wall. It's positive in my direction. And when it moves back, it's going to be the same velocity by conservation of angular momentum, because this thing has an, no angular momentum, I'm saying regular momentum, linear momentum. So this also must be Vx of I, but it's in the opposite direction. One of them is negative when it bounces back, and the other one is positive because the wall doesn't move. So the conservation of linear momentum in here dictates that the velocities must be the same. So it's very simple in this case. So the change in momentum, I'm using uppercase P for momentum. So the impulse, if you wish, of this particle must be, the outgoing is minus mv x of the ith particle. I'm talking about the ith particle now, minus the initial momentum, which is just m times vxi. In other words, it's minus 2 mx mvx in the ith direction for the ith particle. Okay, I'm assuming that all of the particles have the same mass too. That's why I'm not dressing my masses with the index I. So a particle in here, they're all of the same type. The medium is isotropic. The collisions of that matters only are the collisions with the wall, and these collisions are elastic collisions, and basically and the wall doesn't move. So all of these conditions basically give me this expression for the change in momentum or the impulse for the particle. If you are interested in what happened to the wall itself is being pushed with the momentum, because if this one is imparting, this collision is imparting momentum to the particle, the same also impulse is being given to the wall, and that's going to be just the opposite sign, because again, the conservation of angular momentum for the entire system. So this is how much momentum, although the wall doesn't move, but that's basically how much momentum is given to the wall in this case. Okay, so in other words, we need to find the force that this momentum is, these particles are imparting to the wall. That's what the pressure is coming from. That's how we understand the pressure in this case, because the pressure is going to be simply the force, the net force, because we only considered one particle in this case. I didn't consider all of them, divided by the area. So that's going to be my pressure. I'm using the lowercase for the pressure. Okay. So I need to know how long does it take for a particle, or how often does a single particle hit the wall, basically. So if this particle just hit the wall, it's going to travel the length of A and back the length of A again and hit the wall again. So how often this particle will hit? the particle is going to take an amount of time, delta t, which is equal to the distance, which is 2a, divided by its average velocity in the x direction. Again, I'm just talking about the x direction. We'll talk about all of the dimensions soon. So the force from our physics, the ith particle will hit, so this is the ith particle basically, is going to be just the change in momentum of the ith particle over the time it takes to do that change in momentum, and that's simply equal from this expression 2mvx in the I direction, in the x direction for the ith particle, divided by this quantity, which is 2a divided by vxi. This will go upstairs and square that quantity, which is important. Then the direction doesn't matter. If I took the particle in the opposite direction, the squares will cancel, will ensure that I'm dealing with just with the magnitude. The 2 cancel the 2, and I have an expression in here for this to be m over a times vx for the ith particle squared, okay? So this is the force exerted by the ith particle that Mr. Boltzmann made the assumption for. Obviously, I'm not interested in this force by itself for that particle. I'm interested in the net force. So the net force simply the sum of all of this individual forces. That's all. So if I have 1 million particles, add over 1 million particles. Today we know that this number is of the order of 10 to the power 23, of the order of Avogadro's number. So this is a big number. So soon we're going to introduce that concept in here. So this then net force is going to be simply m over a times the velocity in the x direction of the ith particle squared, summed over all of these numbers in here. So I'm going to divide by their number, n, and multiply by their number, where n is just the number of these particles. Okay. That sounds good so far. Well, this quantity is some sort of an average, and it's really the average of the squares of these individual velocities. So I'm going to write it as then, of course, I have n times m divided by a. That's why I introduced the n in here, because this is really an average then velocity. It's an average velocity in the x direction. I'm sorry, it's the average of the squares, not the square of the average. It matters, okay? This is the average of the squares. In other words, the order of the operation matters in here. You have to square first and average squares. You don't average first and then square the averages. So it matters which order you do it. Well, by symmetry, actually the velocity, the overall velocity for the particle is simply equal to squared by the Pythagorean theorem is the x component squared plus the y component squared plus the z components squared. And if I average this quantity, it's going to give me the average for the entire system now. So this is the square of the average, must be the square of the average in the x direction plus the average of the squares in the y direction plus the average of the z squares in the z direction. Okay, so that's basically what it is. But by symmetry, these averages must be the same, because if these particles have no preferred directions, so these directions are all identical. So this must be simply this average, either the vy squared, the vy squared average, or bz squared average, or bx squared. So in particular, these are the same averages, and this is due to the symmetry because of the isotropic properties of the system. Okay, so this vx squared in here is just a third of the overall square, the average of the squares. So in other words, the net force in here is just a third of n times m divided by a. I know m times m has a name, which is just the net mass, because each particle in this case has little mass m, and times m and their total number. So at the end, you'll end up with their total mass. A is just a physical property in this case, which is just the width of this cube that I took in the beginning. Times, of course, the average of the squares. Okay. There is a definition in here which is worth remembering. I know you have seen this concept before, which is the root mean square, which is simply the square root of this averages of the squares. Okay, I know you have seen this one in physics 251, physics 250, physics whatever, physics 1, physics 2. You have seen this average. This is the root mean square. The operation works backward. You square first. Here is a square. You find the average second, which is here, and then you find the square root of everything after you do all of this operation. This is unlike the square of the averages, which is probably going to be 0 in this case because of the symmetry. Because if there is 50 particles moving this way, there's by symmetry 50 particles moving in the opposite direction. And if there are 50 particles going up, then 50 particles are going down by symmetry. So if I'm interested in the square of the average, most likely I'm going to find 0. Otherwise, this gas will be moving in one direction if it has a net average, so in some direction. So you have to be careful in here with this concept, when you're doing statistics. Anyway, so this is the force. We found what that force is. The concept of interest in here is, for me, is the kinetic energy. Before I do that, let me find what this pressure is. So this pressure is then equal to this net force, F net, divided by the area, which is a squared in my geometry. So it's 1/3 of n times m times the square of the average of the squares divided by a cubed, because I already have an a and I already have an a squared, so this is a cubed. And a cubed is nothing but the volume of this expression. So this is v actually. So that means that PV equals to 1/3 of n times m times v squared. This is very, very close to what we need. This is very close to PV equal to nRT. We already find what the product of PV is. I mean, let me a word about the units in here, which is very important. P is a pressure, which is Newton per meter squared. That's what the pressure is, times a volume, which is meter cubed in meters. So this is actually a joule. Must be equal to n. N is just a number, okay? The number of moles. Times R, the units of R, times T, and T is in Kelvin. So this R was introduced for two purposes. Okay, it was introduced to fix the units, which are joules per Kelvin per degree per Kelvin per number of moles, and also to fix the units, to fix the numbers too, so that the units match too, because this is a joule, doesn't correspond to a specific number of Kelvin. So you really have to have that. So you have specific value for it. So that's basically what has been observed. And if you choose the units differently, probably you could choose R equal to 1. So that's not a mystery there. Anyway, so we're almost there. All we have to do is just mass times velocity squared. That's what we know as being the kinetic energy. So this is the average kinetic energy of a single individual molecule or a single individual particle. We didn't know that there were molecules then, but now we know. Anyway, so this is 2/3 then of n times m times, times 1/2. We just introduced the 1/2 in there, times mass times velocity squared, which is the kinetic energy of translation in this case for this, because this is basically the translation. Because we have a point, there is no way for us, because you assume that they're all points in here, so there is no rotation in here. A point doesn't rotate, doesn't spin around anything. Okay, so it's only an idealized situation in this case where there is no physical sizes for it. So the only thing that is of importance in this case is the kinetic energy. So this to be compared to the expression that we know, which is nRT, okay? Well, N is almost related to N because we know that the number of moles by definition is the number of particles divided by Avogadro's number. So I'm going to replace that expression and cancel the two N's in here and see what this thing is telling me. Well, it's telling me that 2/3 of N times the kinetic energy of translation must be, for a single particle in this case, must be equal to N divided by Avogadro's number times R times T, okay? If I fix this N in here, if I cancel this N in here, and I have a new unit in here I'm going to introduce, which is R over NA, and R over NA, I'm going to call it simply equal to KB. I know the book uses the notation K, but the standard notation for Boltzmann constant is KB. So this is just another constant, okay, 1.38 times 10 to the negative 23, because you have the value of R, you have the value of NA, which is Avogadro's number, then you can find what this KB is. So having said that, then I have a relationship between the kinetic energy for a single, basically, particle in this case, in this medium being 3/2 of kBt. Kb times T. So that temperature that we were measuring all along is nothing but the average, basically, with a constant in here of this how fast these particles are moving. So the temperature and the kinetic energy of the individual particles are related through this relationship. That's a very, very important result that we could get to. Obviously, this is just an interpretation of a law that we know by observation, PV equal to nRT. And for that, people took it to a lot of extreme and they started making fun of Mr. Boltzmann to a point that he killed himself at the end. Because there is no other experiments at that time, at least, that confirmed the existence of these particles. So he was basically he was under a lot of pressure because of this, and he committed suicide. His discoveries are still revered by physicists to the point that when physicists remember or go to Vienna, that's what they remember about the most is Mr. Boltzmann. Anyway, so we have this important result that Mr. Boltzmann has arrived to, that the kinetic energy of translation of these particles as they are moving is related to that macroscopic value that we can measure with thermometer based on chapter 17, which is a temperature, okay? Furthermore, if I am interested to find the total energy of the system, the total energy of the system in this case, it's made up of tiny particles and their number is n. All I have to do is just multiply this quantity by n, and I'm in business. So it's simply then equals to 3/2 of, I'm going to go back to the definition of what that n is, which is just the number of moles times Na, and Na times Kb is just R. So I'm just plugging back these numbers in here to find that this is nRT, okay? So that's the total energy of a system, in this case, of this kind, okay? One of the interesting phenomenon that first of all, the total energy is related to temperature, that's all. Okay, so if the temperature doesn't change, the total energy of the system does not change. If the temperature of the system changes, the total energy of the system changes. So the energy of the system is immediately related to that. So what I'm going to do now, I'm going to consider a process where volume does not change. I'm going to call this process an Azokoric process. Okay, so this process, or isovolumetric process, basically the process where the volume does not change. Okay. Anyway, in this case, I know that the system does not do work or have work done on it. Does not do or have work done on it. It does not do or have one work done on it. So that basically there is no W is equal to 0. When the process does not involve change in volume, then in this case, the work is 0. Okay, I think that was one of the questions that you have in the pre-test. Anyway, and I'm going to add heat to the system. So adding heat to the system, in this case, changes temperature, of course. Its temperature will increase. If you extract heat from it, temperature decreases. So if you put it in a refrigerator, what you're doing, you're extracting heat from it. So it was at room temperature, now it's a lot colder, and you can drink your beverage if you like so. Anyway, so in this case, the change in the energy will be just the amount of heat that was added to the system, and by definition, it's going to be equal to the number of moles times the specific heat times the change in temperature. So this is the definition of the specific heat at constant, that's what the V stands for in there, constant volume. Volume, that's an M, okay? So then it's very easy to see from this expression that delta U in this case is equal to 3/2 of NR times delta T, which means that CV in this case, the specific heat, the molar specific heat, because I'm taking it per unit, per moles basically, is going to be simply 3/2 of R. That's an important result for an ideal gas of this type, okay? That's a very, very important result in here. Now, interestingly, if we're not talking about a gas that's made up of this tiny particle, but rather has, because if I go and measure this quantity in the lab, this is easy to do now. All I have to do is just make sure that I have a sealed container and add a furnace, okay? So, and basically be able to measure how much heat is being added, if I know how much the power that is dissipated and so on and so forth. So I know how much energy, how much heat is being added. If I know the number of moles in here, let's take 1 mole to be specific, and I can measure the temperature, T. So I should be able to measure what the CV is. It's very easy. I mean, we can do this in an experiment if we have the proper equipment for it. This is not hard to think about. So we should be able to measure CV. So what observation has shown, and this value of 3/2 of R, it's also a number that we can measure. I mean, what is it? R is 8 something times 3/2, which is about 14 something. So we should be able to get this number, and we should be able to compare the two. This works beautifully for monoatomic gases, like helium, for example, or neon, for example. Impeccable conclusion. However, for example, if I take hydrogen gas or oxygen gas or nitrogen, for example, this does not correspond to that number. It doesn't work. This number is off by a lot. So there must be something else going on. So the way to think about it is the following. For a diatomic gas like this one's in here, what you have in here, you have a molecule or a particle, which is the first H and the second H, and they're connected together via their bonding, okay? So this molecule can move in the x direction with the velocity Vx, can move now as a whole thing in the y direction with the velocity Vy, and can move also in the direction of the z. So I have 3 degrees of freedom in which it can move in terms of this translation, but also it can spin around this axis too, or around this axis too. It can spin around the y-axis and it can spin around the z-axis. Can it spin around the x-axis? No, because they're just dots, so they can't really. Their moment of inertia will be negligible in this case. So if I'm interested in 1/2 of I omega squared, this quantity will be practically 0 around the x-axis. but around the y-axis, it has a finite value. Around the z-axis, it has a finite value. So in this case, I say for a diatomic gas, it has a 5 degrees of freedom, whereas for a monoatomic gas, it has only 3 degrees of freedom. And by the equipartition theorem, in this case, each degree of freedom will bring to us in this expression per molecule, basically 1/2 of kBt. And at the end, this expression will be fixed for a monoatomic gas by 3 times this quantity. For a diatomic gas, we will have 3 plus 2, which is a total of 5 times 1/2 of kBt. So this is each molecule will bring that much kinetic energy into the equation, that much basically amount. So at the end, the expression for a diatomic gas instead will become CV equal to 1/5 of R. In other words, this expression for the total energy of the system for a diatomic gas will be 5/2 of nRT. Okay. The expression, this one is about 20 in the units of joules per Kelvin per mole, and it is exactly what the theory also, what the experiment has shown. So this looks beautiful. Now, the problem arises when we are dealing with a polyatomic gas, for example, if they are talking about the water vapor, for example, H2O, or some other basically gas that you have in mind, then even alcohols and other gases that are that you can experiment with lower temperatures than the boiling temperature, this expression fails a lot, because in that case, the equipartition theorem does not, it will involve other degrees of freedom that include vibrations and other phenomena, and vibrations are quantized when it comes to quantum mechanics. So there are, for polyatomic gases, so for diatomic gases, this is how it is, okay? It's fixed too. As for polyatomic gases, basically quantum effects come into play. Okay, and the quantization of energy in this case involved basically when is the next energy is going to be available or not. I'm going to stop right now here because this is an important part of this chapter, and then we're going to continue to pick up the discussion later on.